Assalamualaikum warahmatullahi wabarakatuh to our beloved lecturer, Dr. Azlin Ahmad. And we are 4A students, and today we are going to present our machine learning final group project entitled Student Grade Prediction. So before that, let me introduce our group members. I'm Nur Syafia Izzati binti Ahmad Tamizi with my other two group mates, which are Syamimi binti Abdul Halil and Nur Kaisara binti Rusli. So let's go to the first part for this project is the data description. So for your information, our dataset named allresult.csv is a dataset about students' previous examination grade that consists data from various subjects such as mathematics, English, and more. In our group project, we want to focus on mathematics grade only. So we want to find a machine learning model that can predict the grades for math subject based on the student's profile. So as you can see, we have 19 attributes and 1037 instances. The problem statement for this group project is to predict whether grade A is assigned accurately to the selected students. Second part is data preprocessing. We preprocess the data using Weka and Python, but first we will explain about the technique used and steps in Weka to preprocess the dataset. So the first step is we remove the attributes that has high unique or distinct values such as PPID. And second step, we replace the missing value before we start discretizing or normalizing the dataset. And for discretization, we discretize the first until the third attribute, which are PP, SEN, EAL into 2 bins and MathX into 8 bins since we wanted to group it into grades such as A minus, B, and more. So after that, we normalize and rescale the dataset in the range of 0 to 1. Then we apply reduction step to the dataset where we remove all attributes that are not related to mathematics. The last step is we use in Weka is hot encoding where we convert string to binary for attributes HML and MA. So next is after removing attribute with high unit value, we replace the missing values using the replace missing value setting. So this is before and after we replace the missing values. Next, we discretize PP, EAL, and SEN into 2 bin, and this is the result for PP. Slide is for EAL, and lastly is for SEN. Next step, interquartile range is used to detect outliers and extreme values. So as you can see before and after the attribute before and after, we remove the value that contains outliers using remove with value setting. So as you can see before removing, we have one value for yes, and after removing it, we have 0 value for yes. So next is for extreme value, but since the yes value is already 0, so there's no need to remove any data with grade A into 1 and the other grade which are beside grade A into 0 since we want to focus on students that get A for mathematics. Next, after discretizing, we select attribute that have no connection with mathematics to remove it. After removing it, you can see we only have 7 attributes with 1036 instances left. We use the one hot encoding method to convert string to binary for HML and MA. So after this step, now we have 26 attributes with no change in instances. So this is the last part that we preprocess is by using Python coding. So after we preprocess in Weka, the value for PP and SEN is in nominal, which is when we import it into Python, it will convert it into a string. But in Python, we can only use numeric values to do modeling. Therefore, we use a library, import random from random, to generate random floating values with range from 0 to 1 for both attributes, and this is the coding that we use to randomly generate the values. Next is, as you can see, the before dataset has nominal value after we discretize them, and after dataset, after we use it using Python coding, it has random numeric values ranging from 0 to 1.
I will explain the neural network architecture design. This is our neural network architecture. As we can see, according to the dataset, it has been automatically generated for our input nodes. So we have 25 input nodes in total, and then we have selected 5 hidden nodes, and we have 1 output node. We will begin our training for model with BPNN algorithm. Firstly, we will import our preprocessed and normalized dataset. We are going to use pandas library to import the preprocessed dataset. Pandas library initially will read our dataset as an object, and then it will display in data frame. The read underscore CSV function will be called in order for it to read the dataset in CSV files. And then we will display the first 5 rows of the dataset using the head function. So this is the coding to import pandas library and to read the dataset. As you can see, this is the number of instances and attributes with the first 5 rows of the dataset. With the second part, we will split our dataset using the train underscore test underscore split function. So we have selected holdout method with ratio of 66 to 33 for splitting our dataset into the training and testing sets. Firstly, we will import the train underscore test underscore split from sklearn.model selection library, and then we will separate the class label into Y data and the remaining attributes into X data before we further split the dataset. We will split the X data into X train and X test, whereby the X train will store all the remaining attributes for training set, and X test will store the remaining attributes of testing set. And then the same process will occur to the Y data, whereby it will split into Y train and also Y test. By default, we should be getting 683 instances and 352 instances for the training set and testing set respectively from 1036 instances. So this is the coding to split the data set for the 66 to 33 ratios. And then the third part is modeling of back propagation neural network. So we have 3 phases in total. So the first phase, we will create class, assigning numbers of input and output nodes, and lastly, initializing networks for hidden and output layers. We created class model BPNN to perform every function in the back propagation neural network. Firstly, we will declare init function to assign parameters into the object self for the class. And then we will assign numbers of input and output nodes using the in underscore n underscore out function. So this is the coding part to assign the number of inputs and number of outputs. The next process, we will be initializing networks for the hidden and output layers. And then we will import random for random to generate random floating values for each network. And the second phase, we will be doing feed-forward, back propagation of errors, and updating weights. So this is the crucial part in training our model. So the first step in BPNN modeling is feed-forward the input layer to the hidden layer. So we will use the feed-forward function, whereby it will accept parameters of network and the current row that is iterating. So this is the coding part. And the feed-forward function will perform the feed-forward in the training. So as you can see, we have separated the values for summation and after calculating the sigmoid function, respectively into zj underscore list and for hidden layer and yk underscore array for output layer. So firstly, it will calculate the summation of initialized network with input and output values, and then it will be performed in the summation function where it accepts the weights and the input values. After the summation value has been calculated, we are going to use sigmoid activation function for every summation. In order for us to perform this, we have to import exp from maths library because we are going to use exponential. So this is the sigmoid function, and this is the final values of zj and yk after feed-forward function has been performed. Please note that zj is for our hidden nodes and yk is for our output nodes. So we will perform our back propagation of errors for output and hidden layers. So in this phase, we will calculate the errors and weight changes for the output layer first. So because as we know that backpropagation of error will move backward, so it will start from the output layers and then to the hidden layers and to the input layers. So the function delta underscore k will calculate the errors for outputs, and weight underscore output will calculate the weight changes of output layer. So this is the coding section for delta underscore k and for weight underscore output. And then the same operation will be performed for hidden layer, but we will be using different functions. Function delta underscore j underscore in will calculate the values that will be used to find the errors in hidden layer, while function delta underscore j will calculate the errors, and weight input function will calculate the weight changes of the hidden layer. This is the coding section for delta underscore j underscore in. This is the coding section for data underscore j. And this is the coding section to calculate the weight changes for input. So these are the final values after backpropagation of error has been performed. So noted that this is only for the first row and in the first epoch. And lastly, we will update the weights for networks in the hidden and output layer. So function update underscore weights will calculate the new weights for each initialized network. So these are the list of updated initialized network for only for the first row in the first epoch. So the last phase will be training the model. So this phase will finally call every functions that have been declared in the class model BPNN using the function train underscore network. So the training will iterate based on inputs given by the user for n underscore epoch, which is number of epochs, l underscore rate, which is learning rate, and also number underscore hidden, which is number of hidden nodes. At this function, we will also calculate the mean sum of squared errors after every iteration of or epoch. So this is the coding section to train the model with assigned values of epochs, learning rate, and number of hidden nodes. So this is the result for the first 16 epochs with its mean sum of squared error values. The reason why we decided to calculate the mean sum of squared errors is we wanted to see the changes in errors for our modeling in every epoch that we perform. This is the testing the train model that we have created just now. Finally, we will begin testing our train model using our testing data set. This will determine whether our predictions will achieve a high accuracy or vice versa. And based on our objectives, we have decided to predict if the student achieves grade A for mathematics. And from the class label, we have assigned all grade A to value of 1 and the rest to value of 0. So this is the coding section for our testing phase. So the model underscore testing function for predicting by comparing the actual values, which is our class table from the data set, and the predicted values from the training model. So at this iteration for each row in the testing set, it will give prediction by comparing the class label and the output that we have calculated. So for every prediction that is correct, it will add up to the true positive. Otherwise, it will add up to the false negative. But for every predictions besides our objective, which is 0 for value of 0, it will add up to the true negative. Otherwise, it will add up to the false positive. So the final result will be shown through the confusion matrix. And this is the coding to calculate and display our confusion matrix. We also decided to show the results for the number of epochs against the mean sum of squared errors through graph representation. We will import matplotlib.pyplot as PLT, and this is the coding to display the graph.
I will explain the result. Next, uh, so first we do confusion metric for learning rate 0.5 and epochs of 100. We do comparison on our confusion metric in Weka and also in Python. Based on Weka, the correctly classified instances is 98.5795%. Meanwhile, in Python, the accuracy on model train is 98.0707%. For incorrectly classified in Python, it is around 1.9293%. We can see that there's a very little difference of accuracy in Weka and Python. According to the confusion metric that we generate from Python, percentage for true positive is around 2.5723%. This shows that when we choose learning rate of 0.5 in epoch of 100, it gives out the accuracy of our objective is 2.57 to 3%. Next is for learning rate, also 0.5, but with epochs of 500. Based on Weka, the correctly classified instances is 98.8636%. Meanwhile, in Python, the accuracy is 98.7138%. According to the confusion metric that we generate from Python, percentage for true positive is around 2.893891. This shows that when we choose learning rate of 0.5 with epoch of 500, it gives out the accuracy of our objective is 2.893891%. Next is learning rate 0.5 but with epochs of 1000. Based on Weka, the correctly classified instances is 98.8636. Meanwhile, in Python, the accuracy is 99.0354%. According to the confusion metric that we generate from Python, percentage for true positive is 2.893891%. Next, this is the graph for every epoch that we use, which are 100, 500, and 1000. So when we increase the epochs, we can see that mean squared error decrease. Now, we use learning rate of 1.0. And for epochs of 100, we can see that the correctly classified of instances is 98.0114%. And based on Python, the true prediction is 97.4277%. According to the confusion metric from Python, percentage for true positive is around 2.250804%. Next is for learning rate 1.0 with epochs of 500. We can see that the correctly classified instances is 99.1477%, and based on Python, the true prediction is 98.7138%. And for the confusion metric, the true positive value is 2.893891%. And last, for the learning rate 1.0 with epochs of 1000, the correctly classified instances is 99.1477%, and for the Python, the true prediction is 98.7138%. And for the confusion metric that we generate from Python, percentage for true positive is 2.893891%. This is the graph representation for every epoch that we use with learning rate 1.0. We can see that when we increase the number of epochs, mean squared error decrease. So for the finding, this is the training accuracy comparison graph using Weka. The blue line is for learning rate 0.5 and the red line is for learning rate 1.0. We can see there's only a little difference between these two. This is the training accuracy comparison graph for Python. For conclusion, after experimenting our train model with several changes in momentum, like increasing the learning rate and number of epochs, we have decided to stop our testing. Based on our observation, the highest accuracy that we achieved was at learning rate 0.5 and number of epochs of 1000. Although our train model is unable to predict the objective that we wanted, which is accuracy for grade A or 1, but it was able to give true prediction for the opposite grade, which is 0, accurately, until it reached accuracy of 99.04%. This might be due to the lack of useful data or information from the dataset itself. In conclusion, our trained model is able to do generalization with changes in momentum. That's all from us. Thank you.